All right, I'm going to talk to you very briefly about the chemistry of fireworks. First of all, a disclaimer. If you're not in my class and you happen to be a chemist or a physicist who is simply skipping through YouTube looking for fun things to work, I urge you right now to cover your ears and hum quietly to yourself and simply tell yourself the video will be over soon. For the rest of you out there, welcome to my non-expert explanation of where the color in fireworks come from. Now, I've already posted a lot of other videos, or linked to a lot of other videos, that explain in detail more information about the fireworks. As a chemist, what I really want to focus on is where does this light come from? What is producing this light? There are two things that produce light in fireworks. The first of these is what's known as incandescence. The second of these is what's known as luminescence. So let's take a look at these topics one at a time by looking at incandescence. Incandescence can be thought of as the color you get when you heat an object. Now, most of us have seen pictures where you take a piece of iron and you stick it in a forge, the flame of a forge. You've all seen the old-fashioned blacksmiths working, or you've seen the marine commercials where they forge the sword out of iron. And you know that after a while, that piece of metal begins to glow and emit different colors. Matter of fact, incandescence can often be defined as as the electromagnetic radiation given off as an object is heated. Quick thing here, we may or may not, depending on the semester you're listening to that, have defined what electromagnetic radiation is. Electromagnetic radiation is all forms of disturbance in an electric magnetic field. Fancy way of saying any source of energy that travels as a wave can be considered electromagnetic radiation. Again, if you're a chemist or a physicist out there, I told you to cover your ears and hum to yourself. But examples of electromagnetic radiation include visible light, IR radiation you've heard about, X-rays, the microwaves, radio waves. All these are forms of electromagnetic radiation. What causes incandescence, though? Why does an object give off electromagnetic radiation when it's heated? It has to do with what actually occurs inside of a solid. We're used to thinking of solids as being exactly that. A substance where atoms are sort of locked into place, and there's very little or no movement going on between those atoms. In reality, the atoms or molecules in a solid are producing a whole world of movement. While they may not be traveling about the town, I like to think of it, the atoms in a solid, as kind of like being two people holding hands. If you've ever watched two little kids hold hands on a field trip, you know that while they're staying close to each other, there's a whole lot of movement going on. And it's the same way for our atoms. First of all, the atoms can sort of move a little bit closer or farther away from each other. Not only that, but our atoms can spin around. Our atoms can twist. So our atoms have, even in a solid where they're locked into place, unquote, quote unquote, they still have a great degree of movement. Anything two people holding hands can do, an atom can do, and more, because I've yet to see two people holding hands where one can turn themselves 180 degrees and stand on their head. Although if you do know somebody who can do that, I want to see the video. So there's still a lot of movement that can go on between these atoms. These movements are often referred to as vibrations. You can also think of an atom moving and vibrating back and forth rapidly. A lot of these vibrations, particularly when they involve carbon bonded to another element, a lot of these vibrations and motions occur along what's known as the IR or infrared spectrum, which is why a lot of the colors that we see are that orange and red color, because we're not able to see with our naked eye all the electromagnetic radiation resulting from the heating of these atoms. But a lot of them occur in the infrared spectrum, and if you've ever heard of a chemist talk about, or in a chemistry show, somebody using IR spectroscopy, it's an instrument that measures the vibrational energy of different atoms in a molecule and is used to determine what elements are bonded to each other. Because each bonding pair, each carbon bonded to a different element, is going to produce a different wavelength of infrared radiation as it vibrates back and forth. Or absorb, rather, a different. Yes, I know, I told you if you're a P chemist, cover your ears. Or absorb a different form of electromagnetic radiation. So when we heat something hot like a metal, we're exciting, so to speak, the atoms of that substance. We're exciting their relationships, right? We've all seen the bad sitcoms where people do something to add excitement to their relationship, such as this clip from The Big Bang.
Amy. Let's wrap things up out there.
Good night, Stuart.
Good night.
Take the hint, Stuart. The lady said good night.
How did you get into my apartment?
Wow. Wait, is that the kind of nagging I can expect now that you're my girlfriend? Good thing I drew this up.
What's that?
I present to you the relationship agreement. A binding covenant that in its 31 pages enumerates, iterates, and codifies the rights and responsibilities of Sheldon Lee Cooper, here and after known as the boyfriend, and Amy Farrah Fowler, here and after known as the girlfriend.
So romantic.
Mutual indemnification always is. Why don't you start perusing while I set up my notary stamp?
Section 5, hand-holding. Hand-holding is only allowed under the following circumstances. A, either party is in danger of falling off a cliff, precipice, or ledge. B, either party is deserving of a hearty handshake after winning a Nobel Prize. C, moral support during flu shots. Seems a bit restrictive.
Yeah, feel free to retain a lawyer.
The atoms in our elements want to add some excitement too. So when we add heat, we add energy in the form of heat to them, their relationship becomes excited, they vibrate a little faster, they lose that energy over time, and they wind up emitting that extra energy in the form of electromagnetic radiation that we observe as red or orange or yellow light there. So that's incandescence. Now, luminescence is something a little bit more in the wheelhouse of this class. A luminescence can be defined not due to heating. What causes luminescence has to do with those electron configurations we were talking about in previous lectures. Remember, the empty space around the nucleus is divided into different energy levels. And electrons are a lot like 2-year-olds. If I have an electron sitting here happily, and I come along and I add some energy to it, that electron acts like a 2-year-old on sugar, right? You get a 2-year-old on sugar, and that 2-year-old gets really, really excited. Same for an electron. You give him extra energy, and he's going to move up to a higher energy level. But what happens to a 2-year-old on sugar over time? That's right, they crash, and they fall back down. And when they fall back down, since energy can't be created or destroyed, they have to re-emit some of that energy. And when that energy occurs in the form of visible light, we observe it. And a lot of the colors we observe in fireworks are due to luminescence. The movements of those electrons excited up from the fuel that excites them, and then falling back down and emitting those colors that we observe. So that, in a 10-second nutshell, is incandescence and luminescence. And we'll go into more detail on the subject of luminescence, at least, in other lectures. In terms of incandescence, unless you're taking my 4 majors class, where I will give you an explanation that won't make the P-chemists who shouldn't be listening now because I told them to cover their ears and hum quietly to themselves a little nauseous. And that's it. Beep.